Multivariable calculus, we're in chapter 14, section 14.2. Take a look at the top of the screen. Today we're going to find limits of a function of x and y, two inputs. And then we can also determine if that function of x and y is continuous. First of all, a limit, well, rather than just see one variable, you can see that I've highlighted we're actually having an ordered pair, x comma y, approach an x naught, y naught. And just as a function that is a single variable can approach a limit, this can happen with a function of two variables. So because we've got two independent variables involved, this does complicate things because we can approach our set point from any direction. In the past, last year and in previous years, we'd have x approaching a number. You could only approach it from the right side or the left side. Now life gets a lot more complicated. A table would really help us out here. Here's function f in table 1. Here's function g in table 2. And we can take a look right here. They're saying, hey, what's happening as our ordered pair x comma y approaches 0, 0? Well, 0, 0 is right here in the middle. We don't even know what our function actually is defined to be at 0, 0. It might not be defined at all. That being said, going all the way around 0, 0, even in a tabular setting, wow, we can be approaching from all different directions. However, in this tabular setting, you can see that regardless of what direction we're approaching 0, 0 from, it looks like our outputs, it looks like our y values are getting very close to 1. So we could pretty much say, hey, what is this limit approaching? Well, we would expect that to be approaching a 1. By way of comparison, if we took a look at function g, this is very, very different in this regard. You can see that as we are approaching 0, 0 here, we're not really getting the same consistent outputs. You can see we might get as large as a positive 1, we might go down to negative 1, sometimes we're at 0. So this would not exist. From this table standpoint, we would definitely say, hey, it certainly appears that we are not having our function approach one specific real value. As we do limits, though, with two variables, it's so very much like what you were doing in the past as you first learned about limits. Very often you can just substitute in. We're letting x get very close to 3 and y get very close to negative 4 without actually equaling that. But this would be 9 plus 16. You could say, look, our output, it appears to be, is getting very close to 25. Likewise over here, if our x is getting very close to 0 and our y is getting very close to a 1, you can see pretty much that we can still have a very good idea as to what our output would approach, what our z value would approach. Well, this is 0, this is 0. It looks like we'd have a 3 up here. Down below, this is 0, and we'd have a negative 1. So, without too much work, you could say, well, it certainly appears like our function is approaching a z value of negative 3 when our ordered pair is approaching 0, 1. But here we go. I'm sure we knew from the very beginning that limits can get far more complicated than just arriving at a set value. When we plug in 0, 0, immediately we get 0 up on top and 0 down below. Further investigation is going to be needed. And, this is what makes life kind of interesting. Just like in AB Calc, BC Calc, we would very often multiply by conjugates. We're still going to do that. We're still going to do that here. So much of multi is really just a revisiting of what we had. So we'll have x squared minus xy, and then we'll have this radical x plus radical y. But down below now, we're going to have an radical x times radical x. That's just an x. Radical y times radical y. That's just this thing right here. And by the way, to help you out a little bit, let's just immediately factor out an x, and then we'd be left with x minus y if we did that. And I think you can see the immediate benefit. This x minus y would cancel here, and then it doesn't take you too long to plug in an x value of 0. We'd have that 0 right up here, and then we'd have square root of 0 plus square root of 0. This whole thing approaches 0. So sometimes you can revisit these problems, do a little bit of factoring, algebra, conjugate multiplication, and get solutions much the same way you did in calc with a single variable. However, sometimes you'll try to factor without success, and this is where we're going to need the two-path test. The two-path test is really a wonderful way of saying, look, we know that we're not forced to just have two directions from the right of an x value and the left of an x value. We could have infinitely many different paths to that point. What we're seeing is, look, if we go along path C1, and if we arrive at a limit of L1, but if we get L2, if we go along a different path, that means that those two limits would not be the same. That means that your limit does not exist. So that begs the question. You can think, well, my goodness, how in the world do we even begin to make sense of this? Well, here, let me show you what we could do. We could say, let's just approach this with curve 1. And by the way, you should always, always, always first substitute in your ordered pair and see what you get. You know, you'd get 0 squared minus 0. That 0 squared, that's a 0. Down below, likewise, you'd have a 0. So, you know, then you should try to do some algebra. We certainly could do some factoring. Unfortunately, the factoring just won't help. You won't be able to cancel things out, sadly. But let's just say curve 1, we're going to approach on the x-axis, and that's kind of like what we see up on the top here. The x-axis is the line y equals 0. Okay, we're going to have y equals 0. And if we were approaching this limit in that mindset, if we were to say, hey, let's just see what would happen if everywhere where we had a y, it was 0. Well, we'd have x squared over x squared, and that would just become a 1. Well, then we could say, well, that's great. Well, hold on. There's more to the story. Let's take a look at curve 2. Curve 2, how about we use the y-axis this time? That's saying let's let x equal 0. And if x equaled 0, well, you get the same basic premise. This time we'd have 0 squared minus y squared. Down below we'd have 0 squared plus y squared. You could see this would be negative 1. Now the problem is you're getting very different answers here. These are not equal. So therefore, this limit does not exist. So this is a nice quick way that we can approach a problem. So letting your curves be the x and the y axes sometimes will help you. Sometimes, by the way, they won't. For example, if you look at this next example, and if you were to plug in 0, 0, you'd get 0 over 0. Curve 1, I mean, we could do the x-axis. We could do that for sure. Let's see what would happen. The x-axis, this is where we'd let y equals 0, and it won't take you too long to see this is x times 0 squared. Down here we have x squared plus 0 to the 4th. Well, you get 0 in the numerator, don't you? And, 0 is going to wipe that out. 0 divided by x squared, you're going to get a 0. Now, by the way, if you did the y-axis right now, you'd say, well, wow, I'd get the same thing. You can even preview it. If you let x equal 0 here, you can pretty much see that you'd get the exact same curve. However, this is the trick to a two-path theorem here. What you want to do is begin to wonder, perhaps I could substitute something in a curve that could be helpful. And dare I say, I'm going to let x equal y squared. Now that might seem to be rather strange at first, but I am deliberately, and sometimes it just takes a moment to see here. If I were to let x equal y squared, then I'd have a y to the 4th down below. Maybe you can already preview that. And simultaneously, if you did that, you could really get some help. So your numerator would also change very nicely. Let's just see what would happen. Look, your x becomes a y squared times a y squared. Down here you'd have y squared squared plus y to the 4th. This is y to the 4th over, well, y to the 4th plus y to the 4th is 2y to the 4th, isn't it? So, we can select this very, very smartly and see then as we cancel, we'd get 1/2. Well, these two things are not equal. So what do we know? The two-path test is a great way to show that a limit actually does not exist. Continuity. Well, to get continuity, a function is continuous. You might remember it's the same three-pronged test that we had in single variable calculus. Your function had to be defined at a particular point. Your limit, as x approaches that first value, in this case a point, exists. And then third of all, very importantly, your limit and your defined function value must be one and the same. So the question is, where would this function be continuous? I think you can see immediately that 0, 0 is a problem. F is not defined at 0, 0. That's the only place where we could break a rule of arithmetic, where our function would not be defined. So we can say immediately then, f is not continuous at that point. Now that's the only location that would cause a problem, where our function would not be defined. Everywhere else it would be, and if you just thought about it, I think you could then see then that your limit, of course, if your function's defined, it's going to be one and the same. So we can actually say that our function is continuous everywhere else. Last one. Here's function g, and you can see this piecewise setup. If x comma y is 0, 0, your function is defined to be 0. Otherwise, it's 2xy all over x squared plus y squared for all other ordered pairs. So you might guess 0, 0 is the big question. Well, we know for step number 1 that g of 0, 0 equals 0. That's right here. So we can say g is defined. The big question, of course, is, does this limit actually exist? And remember, a limit is saying that x, your point really won't equal 0, 0. You can only be close to it. So we're going to have to pick this up in part 2.